So FRQ number 4, part A, it asks us to use the principle of conservation of linear momentum to determine velocity of m1 after the collision. So we know that initial linear momentum equals final linear momentum, which is m2v. We don't account for m1 since it's stationary at the beginning, and then m2v final plus m1 v final, which is signified by the v with the apostrophe right there. So m2v and then equals m2. We're given the final velocity of m2 is v over 2 plus m1 v final. What I'm going to do now is I'm going to add the m2 times negative v over 2 over. So m2v plus 1/2 m2v equals m1 v final. It's giving us 3 over 2 m2v equals m1 v final. And next, all we need to do is just divide the m1 over 2v over 2m1 equals v final, and then that's our answer. Part B, it asks us to find angular momentum omega of this rod after the collision. So using conservation of angular momentum, we know that L initial equals L final. So initially, what's going to cause our rotation is this mass 2 and its velocity times the distance from which it hit in comparison to the center or the axis where it's rotating. So we know that the distance from where it hit compared to the center is L over 3 because we have L over 6. So it's L over 2 minus L over 6, giving us L over 3. So it's mass 2 v times the distance it hit from the center, r equals mass 2 v final, also r, the distance where it bounces back from the center, plus I rod omega, accounting for the spinning rod right there. So we know that m2v, it's L over 3, like that, equals m2. We know that vf is v over 2. R is still L over 3 because it bounces back at the same place, plus 1/12 since it's a rod spinning from its center instead of its end, mass 1 squared omega, like that. Next, I'm going to add this term over. So we're going to get mass 2 VL over 3 plus mass 2 VL over 6 equals 1/12 m1 L squared omega. I'm just going to factor out L over 3, giving us mass 2 V like that, plus 1/2 mass 2 V. That's gonna give us an L over 3, 3/2 mass 2 V, like that. Next, I'm just gonna multiply over 12 and then divide by L squared. That's gonna give us 4 3 mass 2 V like that over 2 and L, because this L gets canceled, leaving us dividing by a singular L, and then 12 times over, and then divide by 3, giving us a coefficient of 4 over there, like that, equals mass 1 omega. We can simplify this as 12 mass 2v over 2l, which is 6 mass 2v over 2l, like that. So since we have that, we should divide m1 over. So omega equals 6m2v. Oh, sorry, there's no 2 right here. Since we divide by 2, it just leaves up a singular 6 on top and then a 1 on the bottom. And then divide by m1, giving us 6m2v over m1l. That's our omega value. Like that. Part C. C asks us to determine the change in kinetic energy of the system resulting from the collision. Okay, so what we're going to need is the initial Ke value. So it's only Ke linear. The Ke initial is only consisted of Ke linear. So we know that's 1/2 m2 vi squared, like that. And now for after the collision, we know that there is 2 Ke linears. There's going to be the Ke linear of mass 2 traveling back, and then the Ke linear of the rod traveling linearly like this, but there's also going to be a Ke rotational as the rod rotates as it's traveling linearly. So what I'm going to do is I'm going to figure out the 2 Ke linears, final Ke linears first. So we have 1/2 m2 v final squared plus 1/2 m1 v final squared, like that. That's going to equal 1/2 m2. We know the v final of m2 is negative v over 2 squared plus 1/2 m1. And we know that the v final of m1 is the v we found right here. So we're just going to plug that in. 3m2v over 2m1. And then we're going to square that, like the formula says. So simplifying all of this, this is going to turn into v squared over 4. So we bring the 1/4 in the front, so it's 1 over 8 m2 v squared plus 1/2 m1. This is going to be 9 m2 squared v squared over 4 m1 squared, like that. Next, we're just going to cancel out the m1 right here, leaving us with a singular m1 on the bottom. So that's going to give us 1/8 m2 v squared plus 9 over 8 m2 squared v squared m1, like that. And then that's our Ke final in respect to linear. Now we're going to find Ke final rotational, which is going to be with the rod. So it's going to rotate from the center. So it's going to be so the formula for rotational Ke is going to be 1/2 I rod omega squared. 1/2. We know the I of the rod's 1/12 spinning from its center. That's 1L squared omega squared, like that. Since we found omega already, we can plug that in. 1/12 m1 L squared 6 m2 v over m1 L squared. What we're going to do now is we're going to simplify that. Bring the 1/12 up to 1 over 24 m1 L squared 36 m2 squared v squared over m1 squared L squared, like that. Next, we cancel out the L squareds. We cancel out the m1 right here. And then simplifying 36 over 24 leaves us with 3 over 2 m2 squared v squared m1, like that. Okay, that's our final Ke rotational. So to find change in Ke, it's going to be Ke final minus Ke initial. So we're going to add all the Ke finals together, which is going to be the Ke final linear plus Ke final rotational minus the Ke initial. So it's going to be equal to 1/8 m2 v squared plus 9 m2 squared v squared over 8 m1. That's going to be our k final linearly, plus 3 m2 squared v squared over 2 m1. That's our k final rotational minus the k initial that we found is 1/2 m2 v I squared, like that. So what I'm going to do right now is I know that these two have common terms, so I'm going to subtract them. So 1/8 minus 1/2 leaves us with -3/8 m2 v squared, like that. So we subtracted 2 of these. These two have common terms, so we're going to add them together, get common denominators. So we multiply this by 4, so it's going to be 12. The coefficient is going to be 12/8. So we add the 12 with the 9, it's going to be 21/8, like that. M2 squared v squared m1, and then that's our change in KE after we simplified everything. Thank you.